Hello, I'm Mr. McBrien. This is TEJ20, Introduction to Computer Engineering. So, you decided to take this course, or at least you decided to click on this video. So I'd invite you, before you go any further, to pause and ask yourself, why? Why did you go to that trouble? Why do you think computer engineering is interesting? So go ahead and pause and think about that for a second, and then come back and we'll talk about my perspectives on this. Okay, welcome back. So my perspectives on this have to do with, first, setting a context. So in 1947, something amazing happened. The transistor was invented. So Bardeen, Brattain, and Shockley together invented the transistor, and they described the transistor effect as this: when electrical contacts were applied to a crystal of germanium, the output power was larger than the input. Now, this is an intriguing statement, and we're going to dig deeper into this later when we unpack the transistor completely. But for now, I'd like you to think just in terms of the idea that the transistor formed the capacity for switching and amplifying that forms the basis of every electronic device that we've invented since, essentially. Okay, so that happened in 1947. Ancient history from even my perspective, let alone yours. So why go back that far? Well, the answer lies in this: Moore's law. So Moore in the 60s was involved in computer design. Does anybody know, maybe think about, do you know, or have you ever heard of Moore's law? Well, it was essentially this. He made the observation, it's not a real law, it's an observation, that about every 2 years the number of transistors on a chip doubles. And this implies that computers double in speed every 2 years, or double in power every 2 years. Or it implies that a computer with the same performance can be roughly half the size after a 2-year period. And this might not seem like that big a deal until you start to think about the amazing things that can happen with doubling over that many years, over decades. Remember, this means that the capacity of a computer doubles multiple times every 10 years. While you're in high school, it'll in fact double 3 times almost. So that's not all. Other advancements in computing that aren't this incremental advance can also improve on those numbers. So here's an illustration of something close to Moore's law. It isn't the number of transistors on a chip, but it's closely related. This is a USB flash drive, a 512 gigabyte drive. What's intriguing about that? Well, that amount of storage space that you can carry around in your pocket and buy on Amazon for next to nothing is the equivalent of about 10,000 times the capacity of my first hard drive on my computer. And I paid for an upgrade, a $500 upgrade for that computer to have additional hard drive capacity. This astounding change in technology can do some incredible things. So this incremental improvement can trigger revolutionary applications. I'd invite you again to think of examples of this, but maybe the most prominent is the idea of a computer that 30 years ago would have had incomprehensible levels of performance can now be purchased as part of a telephone plan and carried around in your pocket. But there's more to it than that. There's more to it than just having computers be portable and accessible. When we have processing power available to us, we can start to do things that were previously done in very, very different ways. So in 2007, the Stuxnet worm began its attack on Iran's uranium enrichment facility and, by most accounts, delayed that nation's nuclear program for a considerable amount of time. Stuxnet was amazing because it infected computers all around the world and still continues to do so today. But it was smart enough to target the programmable logic controllers associated with the Iranian nuclear program. So in fact, it was a targeted worm. An amazing thing. Now, what's amazing about this is that had this been even 10 years previous, instead of an intelligent attack using simply zeros and ones, probably there would have been jet fighters and missiles involved blowing up those facilities with concurrent loss of life, etc. Now, 5 years later, Curiosity landed on Mars and for more than 4 years traveled around an unmapped surface of that planet, even though the team that was nominally guiding it was out of communication for more than 90% of the time and never had the opportunity to really react quickly because of speed of light issues. 4 years after that, Ontario approved the first automated vehicles driving on their roads. And that pilot project implied that the car that passed you on the highway just might have no one at the wheel. This doesn't seem that strange to us, even 4 years after that. So, what do these things have in common? They all have machines making intelligent decisions for us without us being in direct control. And we might ask ourselves, how do we make devices smart? How do we make thermostats smart? And this is one of the most interesting challenges we have as computer engineers. So, what is computer engineering then? It is the integration of devices, electrical engineering, and computer science, programming. So it's robotics, it's automation, it's decision systems, it's sensors, it's device design, it's computer design, and computer repair as well. What kind of skills do we need? We need to be able to analyze problems effectively. We need to design systems to cope with those problems. We need troubleshooting and logic when things go wrong. We need to be able to construct circuits and also analyze them. And we need programming for both analytics and decision support. And all of these things move us towards building projects and the project management that goes with that and the documentation that goes with it. A lot of skills. And let's not forget mathematics as well. Now, more than anything else in computer technology, my objective is to have the student start looking at any object, any device, and stop viewing it as something that does something, and instead start trying to say, how does it do that? How did they achieve this? So we want to be taking the covers off of devices to see what's inside when it's safe to do so. We want to try to look at circuits and say, why do they do the things they do? We want to take a black box and reject that concept completely and say, I want to know what's going on inside. And when we can understand what goes on inside, we can start to design our own devices that people can take for granted. So our foci in this class, we'll talk about careers in computer engineering, what you can do with the skills you have. We're going to spend a lot of time talking about circuits, spend some time talking about design and documentation. We'll look at computer hardware. We'll spend a great deal of time on programming and automation. Your evaluations, the place where you'll get your marks from, will have various unit tests and quizzes, lots of hands-on projects, a careers project. We'll spend most of the last month of school working on our summative projects and a final exam at the end. As far as submissions go, we want to try to stick to electronic submissions wherever possible. Obviously, some projects will have to be submitted in hardware form. But wherever possible, we'll submit through Google Classroom and or Brightspace in electronic form. We won't be submitting via email or hard copies, with very few exceptions. And when you share your Google Drive documents with me, that should be through the link on Classroom. This makes both of our lives very easy. Okay, key points then for today. Computer engineering, computer technology, they're about making devices smart. Because of Moore's Law, because of robotics and automation that is in the forefront today, this discipline's in considerable demand. Hardware design itself rarely occurs without software being developed for it. In TEJ2O, we're going to focus on all aspects of this. So on design, on electrical engineering, and on programming. Now, our activity for today, I'd like you to work in pairs if you wish, or you can work alone. And view the Astounding Athletics of Quadcopters video TED Talk. And while you're watching it, consider which inputs were used to sense the environment. Consider the physical models used to customize behavior of quadcopters for specific purposes. There were several purposes shown in the video. And consider how machine learning was used in the implementation. So you may have to view it a couple of times in order to get all of that information out. So for your homework, go ahead and finish the documentation of the quadcopters material for discussion tomorrow. Make sure you sign up on Google Classroom using the code you were given. And be sure that you get your contact information and consent forms filled out. Thanks very much, and have a great night.